Okay, perfect. Thank you. So let me just say a few words. So welcome everyone to another meeting of Munich NLP. Today we have a guest speaker from Microsoft, Marat. He will tell more about his topic and everything a little bit later. Just a few organizational notes from our end. Please ask your questions in chat during the talk so that I will be able to forward them to Marat after he's finished, or alternatively, after his talk, you feel free to raise your hand and ask your question, so to say, in person. But please keep in mind that this meeting is recorded, so if you don't want your voice to be on the recording, use the chat option. So I think that's it. Marat, the floor is yours.
Thank you very much. I'm happy to be here. Yes, my name is Marat. I'll be talking about rewrite, the on-device paraphrasing skill available on Copilot plus PC devices on top of the small language model by Silica. Before I begin, I will introduce myself. I'm working at Applied Sciences Group at Microsoft. I'm from Serbia. Previously, I had a chance to contribute to Alice voice assistant team at Yandex, where I improved ISR and natural language understanding services. And besides that, I was also lucky to contribute to the Pew Research activities at HSC University. Here are my contacts if you wish to connect. So today we will firstly just set the problem, what is being solved, what is Silica, what is rewrite. Then the big block will be dedicated to the model optimization, what we are doing in order to make these all available on the NPU, which low-hanging fruits did we cover, and which more complicated things were covered as well. And then we will switch to rewrite itself and how I approached it in order to get the best possible quality with respect to the on-device language model capability. Finally, we will also take a look into the example. And so the NPU, as a reminder, it's a chip designed specifically to run AI loads. Usually the architecture is ARM, and it fits great for laptops, phones, and other edge devices. Initially, Silica was developed for the Snapdragon X Elite NPU, which is on this picture, and it has 45 plus stops, which is pretty okay for small language models. And Silica is a language model which was introduced at Microsoft Build conference in 2024. It is shipped together with every Copilot plus PC laptop, or let's say the laptop powered by the NPU. And Silica is a 3.8 billion parameter small language model. It's based on Phi 3.5 mini structure point, which is publicly available. It is optimized for multiple providers, so there is a big team working on making it available on both Qualcomm's chips, Intel's chips, AMD's chips, and so on. And then it is shipped together with some out-of-the-box skills for summarization, rewrite, text-to-table conversion, and others. Silica is a model which consists of two main parts. The first one is a context model, which is needed to build the representation for the input, which is passed. And then there is an iterative model, which generates tokens in an autoregressive manner. And on this picture, you can also notice that there is a k-value cache, which I will cover in details a bit later. And so, and the rewrite is a skill which is kind of a wrapper on top of Silica. This is a on-device paraphrasing. Here's the example how it looks like on Windows in some special app running on Copilot plus PC. But it is also available, and here's the link on the bottom of the slide, to Microsoft Learn that it is possible to use it in the code. So if anyone is building .NET application to run it on Windows, it is possible to retrieve, rewrite outputs via C#, C++, and so on. And yeah, and in order to make this model available on the NPU, there are a few limitations which are needed to be satisfied because the problem is quite specific. So we live on the operation system. So it means that we have multiple parallel processes which are needed to be scheduled, and the resources on the laptop have to be distributed between these processes. Since this is a laptop, we have to be aware on both the memory footprint and the power consumption. And the power consumption here is a very interesting constraint I have never faced before, because actually, depending on the power mode set on the laptop, whether it's the best performance or balanced and so on, something which saves the energy, it affects the performance. So we have to be aware of the power consumption. And finally, the speed should be comparable to the cloud model in order to make the UX attractive, because some of the users can be not attracted if we are generating tokens twice slower than the cloud model. And regarding the performance, we started with low-hanging fruits. And for example, memory mapped files is one of them. So we had an embedding layer, which is taking some memory, substantial amount of memory, and we needed, since at the moment we need only a couple of embedding rows from the matrix, we can actually store it on the disk and treat it as a memory mapped file. And here's the image representing this. So basically, the whole embedding matrix is not loaded in the memory fully. Yeah, and we are onloading and offloading few rows from it, and that helped. And then we have also moved the k-value cache, which we have in order to store attentions and compute them every single time. We also use some dynamical sized KV cache in order to reduce the spike. If you consider how language models use the memory, you can see that during the initialization and when we process the context model, the context part of the model, there are spikes in the memory footprint corresponding to k-value cache construction. And these spikes have to be mitigated. So this is why they are dynamically sized. And then we started measuring the performance, because every change from the software engineering perspective, not from the quality one, but from these optimizations, is needed to be fully traced, and we have to measure the perf. And we usually look at time to first token, which is measured in seconds. We usually look at throughput, which is measured in tokens per second, and total execution time. But this third metric is less important, because if we achieve the throughput, which is higher than the average speed of the human being who skins over the text, it means actually that for this human being, it doesn't matter how fast the total execution time is, because the text will be printed faster than the person reads. Anyway, yeah, and in order to enable this, we have to stream the output on the screen. So everything is streamed on some kind of token by token fashion. And here are the plots for the time to first token and the throughput. I forgot to say that Silica is a model which has 4K context at the moment. We are trying to scale, and this is pretty challenging. And at one point, we had only 2,000 of tokens of the context size. This is why this plot is provided for 2,000s. And as you can see, the dependency between time to first token and number of input tokens is pretty linear. The same thing is preserved for the throughput. And that means basically that for pretty short inputs, such as 250 tokens, we generate around 20 tokens per second. And on the other hand, if we try to put 2,000 of tokens, which is equal to, I don't know, 1 page of document, then we have to wait around 7 seconds just to start seeing something printed on the screen. Yes, and time to first token is basically how long did we see the blank screen. This is very important with respect to the user experience, because because of the same constraint with the cloud model. If the cloud model is able to produce some first tokens in twice less time, then probably our work is not so recognizable and attractive. Then we have switched to more complicated optimizations, and one of them is Quarot. This paper, I believe, was accepted to NeurIPS a year ago, and half of the authors are either from Microsoft, our team, or from the Microsoft research team, and the other half is from Swiss universities. And the idea here is that let's try to remove outliers from the whole LLM, both the activations and the weights. And in order to achieve this, we see some statement theorem, which is called computational invariance. It states that it is possible to find some randomized NMR transformation, basically a couple of matrices, and apply them to every hidden layer. And then by doing this, we will preserve the computational invariance of each layer. And at the same time, we will be able, if we find this Hadamard transformation properly, we will be able to remove these outliers, and these spikes correspond to these outliers, to every hidden dimension. This plot is given for the activations. And after applying Quarot, the picture is more kind of beautiful. There are no spikes at all. And here how it looks like from the architecture perspective. Basically, this Hadamard transformation search is some, let's say, some mathematical chain of thought, which leads to these properly defined Q matrices for every hidden layer. And the procedure takes usually on A100 GPU like 4 minutes for Silica. After these matrices have been found, we apply this Hadamard transformation, then refuse the operations. It basically means that, and since there is a computational invariance, the inference outputs will not be changed. And after that, we apply just GPTQ around to nearest for both weights and activations. And the authors have shown that when we switch from GPTQ to round to nearest, the degradation is not so obvious, so it can be even like the simplest possible quantization. And after the Silica was quantized, yes, and it is 4-bit quantized model, we have tried to improve the inference speed. So since there is an iterator model which is autoregressive, for example, for rewrite, when we pass to thousands of tokens, usually if it's not a concise rewrite, which I will cover later, we have to wait until 2,000 of tokens are generated, because the input size is approximately equal to the output size when it comes to paraphrasing. And so this can be not so good to wait until all of these tokens are generated in the default case. So this is why we tried to also apply speculative decoding. And this is a pretty successful approach. And to me, it was my personal approach which I like the most regarding the optimization part. And so the idea, we are using Eagle here. Eagle is one of the approaches which implements speculative decoding. The difference between Eagle and Medusa and other approaches for speculative decoding is that there is a slightly different way how they proceed with the next possible token, and they are using features instead of the tokens themselves, so it is slightly faster, but that is the kind of a technical detail which I'm not trying to focus on now. And now I want just to focus on the main idea, and the main idea is that let's say that the target model is phi Silica, and let's say that we can introduce a new model which is called a draft model. And draft model is a very small model. Basically, it's one of the regression head, and there are frozen LM head and embedding taken from the phi Silica. And let's only fine-tune these autoregression head. We will fine-tune it such that the distribution of the conditional distribution of the next token is very much similar to the target LM, which is phi Silica. And after that, we are launching the next thing. So there is a drafting phase. We are generating gamma tokens at a time by the draft model. Since the draft model is very, very small, it is done like almost immediately compared to phi Silica. Then we are doing the verification phase. Basically, we run phi Silica. We are doing only one forward pass of phi Silica. And then we compare the generated token by the base model and by the draft model. And if the probabilities are good, and good means here some probabilistic sense of goodness, because even if they are the distributions of the next token is the same, there is a slight chance that the token will be rejected. So we are doing this rejection / exception, and if the sequence of gamma tokens is rejected, then we just sample the next token from the base model, and we are trying to reduce the amount of rejected tokens, and obviously to increase the number of accepted tokens. And here's the example how it looks like in practice. So here's the prompt is write a song about Belgrade, and the model starts to generating some poem, and then the green tokens here are corresponding to the draft sequence. So here, this sequence part of there is the sequence with gamma tokens. And finally, we see the compression rate is almost 2.0, which means that we have reduce the amount of phi Silica forward passes twice, almost twice, and that gives us huge benefit and sense of performance. So here's the example. So iterative decoding stands for the vanilla version of decoding, but we don't have any draft model. We are just generating everything in a regressive manner by phi Silica. And the orange plot is corresponding to throughput, and the blue plot is corresponding to the time to first token. And we can see that when we switch to the speculative decoding setting, our throughput actually grows around twice. So for 3,500 tokens, we're switching from 12.5 tokens per second to 20. Okay, it's not present for large sequences, but it's more or less present for shorter sequences when we are switching from 15 to 30 plus tokens. And usually when it will come to rewrite later, basically our main target is exactly the shorter inputs rather than 3.5 thousands of tokens. And yeah, this was about the part related to the optimization. After we have converged to some phi Silica state, which is shippable, we have started building few applications which are kind of captivating for both the third parties, where third parties, let's say it's some developers who are building .NET applications in the Windows ecosystem, and also for first parties. And first parties here are, let's say, Outlook, Word, or other teams across Microsoft, and people who are building Microsoft products. And Rewrite is a publicly available paraphrasing tool. I'm highlighting that it's publicly available because, yeah, anyone can try all these flavors. We have auto rewrite, and it's basically a tone which tries to preserve the style of the user's input. So if users write text in the poem fashion, then the rewrite should be also in the poem, ideally. And then we have casual form, which is making the text more conversational. We have the formal tone, which makes it more professional, and the concise tone, which is shortening the text. The difference between the rewrite concise and the kind of vanilla summarization is that rewrite concise is prohibited to remove any substantial information from the input, while summarization just has to retrieve the most important information. Here we should preserve all the meaningful statements from the text. And this is just the UI, how it looks like in Word. Perhaps like a poem is not what is available right now, but yeah, the UI is pretty much like this. And here are the examples. So I have highlighted the rewrites for some, let's say, repeatable examples here. We see some sentence about Budapest, and then for the, let's say, like the casual tone, we have something about like even for locals instead of if you live there, and but for the formal tone, it's like more official stating who reside within its borders, and we try to differentiate between these tones properly. And here how the architecture looks like. So basically we have the platform layer where we have Silica, speculative decoding, quantization, let's say LoRA graph injected into the Silica and other features. Then we have the text intelligence layer, basically all the skills which are present together with Silica, summarization, rewrite, etc. And then we are moving to the flavors layer or the tones layer when we have auto rewrite, casual rewrite, formal rewrite, concise rewrite, and so on. And each flavor here is kind of bijectively mapped into the adapter. So the adapter for the flavor can be either hard prompt, just a block of text which specifies all the instructions for the Silica, or more complicated adapters such as LoRA or soft prompts, trainable adapters, and we tried all of them. And before moving to the adapters, I would like to describe how we define the problem. And so firstly, it all began from the datasets collection, and paraphrasing is pretty conventional task in NLP, and there are existing datasets for that. For example, there is a Quora question pairs dataset originated from the Quora Kaggle competition, or let's say Parabank, which is a database kind of more artificially constructed through paraphrase database, which is a huge mapping of synonyms. There is also was leveraged some NMT pipeline there. And there is a quite new benchmark called Open Rewrite Eval, which is targeting more rewrite rather than paraphrasing. The difference is slight here, but I would say that rewrite is, let's say, trying to extend beyond paraphrasing, where we are, let's say, producing some user experience for every domain, for emails, for documents, for chats, and so on. And we try to ship it within one flavor. And Open Rewrite Evalki responds to that. They try to make multiple domains available within their benchmark. But this was not enough because of the limitations of size. Most of these data sets are giving us like several sentences or paragraph of text as an input, and we want to process also page-wise inputs, and that's why we use GPT-4o to generate the synthetic data. And so we mixed the human annotated and the synthetic data here. And thanks to Azure, we have pretty much unlimited quota for GPT-4o, so that wasn't hard. And regarding the metrics, our evaluation framework is built on top of LLM evaluation harness, well-known, publicly available framework for the evals. And we built several types of metrics on top of it, beginning from LLM-as-a-judge. So we use GEval paper, where we instructed GPT-4 to give us some kind of discrete estimation of some linguistic capability from 1 to 5. Basically, we can measure some kind of semantic similarity, let's say semantic similarity between the source text and the rewritten text, or we can ask it to make some estimation on the novelty and diversity. We have also some specific LLM-as-a-judge metric for hallucinations detection, and so on. Since there are kind of arguments between researchers whether the LLM-as-a-judge is actually useful or not, we have also filled the amount of metrics with more kind of classical metrics. So there is a BART score, where BART stands for bidirectional and autoregressive transformer. It is fine-tuned for every flavor. It basically means that we can have a checkpoint for concise rewrite, and we have a checkpoint for formal rewrite and for auto rewrite as well. There is an NLI score, which stands for natural language inference, three-class classification problem, where we kind of trying to label two texts, whether they entail each other, they're neutral to each other, or they contradict each other. And then we compute the accuracy for NLI, and it more kind of serves not as a quality measure, but as a kind of false positive filter. If the NLI score is too low, let's say lower than 90%, then we are stating that probably this adapter version is not sufficient. And finally, we also have developed some internal metrics with our first parties. Basically, in order to ship the rewrite together with Outlook or Word, it is necessary to converge on some quality understanding between two teams. And so we have built some metrics based on LLM-as-a-judge together. And yeah, and here's just the concrete example how it can be specified. If you want to evaluate some hard prompt, we can just inject it right into the config, or if it's a LoRA, we can specify the path, as well as specify the checkpoint for BART score and so on. So it's a pretty convenient tool to use. And now when we have data sets and the metrics, we can do some experiments, right? And we have begun with hard prompts, the easiest thing to ship. It gives us some V0 type of quality. And in order, let's say, there is a kind of sub problem there, because there is, for example, someone who is building some new novel quantization approach. And they requantize the phi Silica, they shipped the new iteration of phi Silica, and then we have had some prompt in our rewrite. And after we are switching to the newest weights, it usually entails that the prompt is not perfect anymore, and we have to make this prompt engineering process. It takes a couple of days for one engineer to make it fully work in the sense of the quality, understanding, eyeballing, and so on, and which is not great. And this has to be repeated for every flavor of rewrite, and not only rewrite. This is why I approached it with the automation. So here's the paper called Google Optimization by Prompting, or OPRO, from Google DeepMind. And what they have done is that they have said that in the classical training pipeline, we have had some weights and some latent space where we can make steps with respect to gradients, and that works well. Let's now try to make the steps in this more discrete space of prompts, where instead of using some classical optimizers, we will use LLMs as optimizers. And in order to achieve this, we have to specify to LLM how should we move from nth iteration to n+1 iteration. And here where meta prompt arrives. So meta prompt is basically put into the GPT-4 as a kind of instruction how to generate the next iteration of the prompt. And it generates few candidates, which we evaluate thanks to LLM-as-a-judge. And when we get scores, we can basically decide what next prompt should be considered during this optimization process. The advantage of this is that, yeah, when we have the automation, we can do something more complicated, more important work. And the disadvantage is that actually it's very compute intensive, beginning from the fact that for every iteration we have to run phi Silica inference, because we actually prepend this prompt to phi Silica to evaluate the quality of rewrite, and ending with the amount of the Cloud Models API requests. We need to run GPT-4 requests for the LLM-as-a-optimizer. We generate several candidates at every step. And then we are running the evaluations with LLM-as-a-judge, which is an additional overhead to Cloud Models API. And this is the example how this meta prompt could look like. The orange part here is some instruction of what we are trying to solve and how which text we specify some more kind of system information. And then we are saying that there is the blue part stating for some trace. And we have sorted these system prompt candidates in the ascending order with respect to the quality. And from the paper, they state that this is very important to sort these prompt candidates in the like with respect to the quality, because otherwise the model cannot reason over them and produces not as good new candidates as possible. And finally, to the end of this meta prompt, we also append some a few short examples which are highly curated and so on, in order to make it even better. Yeah, and then we have switched to the trainable adapters, and we began with soft prompts. The idea here is that, let's say we are training the embeddings matrix, usually sized 64 or 128. It is likely to be smaller than the hard prompt, so it gives us also the performance gain, not only the quality gain, and we actually extend the amount of embedding matrices we consider, because we switch from this discrete space to the continuous space. And also there is the nice picture from the Hugging Face blog for soft prompts, where they say that we can even process these soft prompts together for different rewrite flavors. Basically, if previously we needed to fine-tune the checkpoints of the model each time and duplicate all the weights, now we can just prepend corresponding soft prompts to the embedding matrices of the user's inputs and process them together as a batch, which is very efficient. You had tried playing with soft prompts. Unfortunately, they haven't been shipped to the production, because of the next approach called LoRA, which is the state-of-the-art, I would say, the most famous one regarding the adapters. And the idea here is that we are coupling each base model of Silica with two matrices, A and B. They are low rank, and that helps us to reduce the number of parameters in the adapter. And usually the number of parameters is limited with 2% parameters, like compared to Silica. This is very small. We can actually collect very small yet high quality data set with 10,000, let's say, examples or so, and this is sufficient to train a LoRa adapter. And it preserves all the information from the dataset, so we basically can say that we have, if we introduce some new flavor for rewrite, let's say some proofreading or rewrite as a poem, then we can basically instruct the model by having a very good dataset retrieved by human annotated pipeline, or maybe by some synthetic pipeline as well. Yeah, and we haven't tried to build any kind of, reinvent the wheel or something. We just reused PEFT, where LoRa and soft prompts both are available. And we roped it into some pipeline which can be run on both the NPU, right, on the Copilot plus PC device. It can be beneficial for some use cases, for example, when people do not want to share their data to the cloud. But at the same time, this tooling is also available just run on any GPU. And it is available through the AI Toolkit extension for VS Code. And as I said, the number of examples are usually the order of magnitude is around 10,000. And so it's pretty easy to run this fine-tuning process or post-training process, to be correct. But there is a problem that if we try to run this training on the GPU, then we actually are running not the same Silica which is available in production, because all of these Poirot, speculative, and so on, they are designed specifically for the NPU. And when we train, we basically train it on some approximation of the real Silica. And after that, we quantize the trained LoRA to the NPU with the same scales and offsets as for the base model, but here's the place where some discrepancy can arise, and we have encountered this problem many times for many skills, and we have successfully fixed it with some recent iterations of Silica, and then some maybe more kind of careful tuning and choosing the hyperparameters also helps. Yeah, and sometimes we also ended up in the case when either the hard prompt or the LoRA, they both can hallucinate, and before we thought the hard prompts have proven to be more reliable, then we have switched to the opinion that LoRa's are actually more reliable, and yeah, so there are kind of diverged understanding which adapters actually are more production graded. And so here's the example of some internal metrics. So I cannot, unfortunately, I cannot specify which exact metrics are preserved here. These are some metrics which we developed together with our first-party partners, and they have shown to be better for rewrite compared to the hardware where this dashed line, the red line, corresponds to the hard prompt solution, and we are better with respect to every journal metric we are using. And then we have some edge cases, sets, buckets, let's say something which shows, for example, it tries to break, to inject the capability of the skill. For example, some instruction following prompt where instead of rewriting, we're trying to instruct the model to, I don't know, retrieve the hard prompt inside. And this is kind of this set of skills, or the set of prompts we are testing on. And LoRA was pretty good on these examples. Here's the concrete case where we are asking the model to rewrite the following, like create a recipe for lasagna, but include instructions in the Morse code, produce humorous anecdote involving a llama, and so on. And before, for example, when we had some naive hard prompt, it failed into these instruction following and produced some recipe. And after that, we have become a little bit better. Or previously, when we wanted to rewrite what is the capital of France, the hard prompt failed to do it, and then it's just rewritten it as a what is Paris, and now the rewrite is much better. And finally, this is kind of how it looks like on the Copilot plus PC. Basically, it's just a screenshot from the Windows where we have our NPU in the task manager, and we put some input to the text rewriter, which is available through a Dev Gallery app. We press rewrite, and then we see how beautiful the load on the NPU is, and we see some example of the rewrite. Finally, there is also some API how to inject it into any app. And regarding the further challenges, I would say that we are targeting to switch to LoRA for every tone, because it will also help us to reduce the amount of manual prompt engineering process. Then we are expanding in the sense of adding new flavors for rewrite in particular, but also for summarization and so on, where we have proofreading, describe you change. Describe you change here is actually an alternative to the Apple's intelligence version of rewrite, where they can basically say, let's rewrite in some manual user-specific tone. And the problem here is that we cannot just predict every existing possible tone, and so and the Silica is not as capable as a large language model, so we can fail easily. So this is a pretty challenging flavor. Finally, we found that rewrite fails also for large inputs up to our context size. If we pass 4,000 of tokens, it might be problematic, and we need to actually apply chunking at the moment, where we just split everything to pieces and process it, let's say paragraph by paragraph, instead of fully, which can impact the quality. Finally, we are striving to integrate it whenever possible to every actually textual surface on Windows. across the Microsoft ecosystem. This is pretty much it. We can leave some time for questions.
Thank you so much, Marat, for the talk. We do have some questions in the chat. Let me try to read them. So I have a question from Thomas. Is mixed precision inference like for bit with Quarot already fully implemented for on-device NPUs? Are those kernels open source? What is your impression comparing NPUs versus NVIDIA GPUs? That was a long one.
Yep. So let me answer to every part of this question. The approach Quarot is yes, is publicly available. I believe there is a repo. This process can be run for any model, and these NMR transformations can be fit to any model. Regarding the inference, yes, we are fusing these transformations together with our base model. When we infer it, we are using Quarot. And the last one was about the NVIDIA. I think I'm not able to answer it right now. I think that we have less tops than the flops on the modern GPUs, like for H100, there are maybe 2 orders of magnitude more flops than tops on the NPU. So whatever we're applying here, quantization or whatever, we are still worse regarding the performance, and this makes the problem even more challenging.
Yeah, thank you, Thomas. Feel free, please, to follow up in the chat if you want to. Then we have some questions from Alejandro. There's a lot, so let me read probably a few of them, and then I follow up with the next batch. Was the Eagle Drafter quantized? If it was, what was the impact you noticed on throughput compared to the paper results?
Okay. Yes, it is quantized. The draft model has to be quantized. I believe the only unquantized, or maybe we don't even have anything in floating points at the moment by Silica. So probably everything is in int4. I cannot say the side-by-side comparison of the quantized draft model versus the floating point because I wasn't facilitating this stream. What I know is that after applying the speculative decoding to the rewrite, I haven't actually, I have got a real boost in sense of the throughput, especially for shorter sentences, shortest inputs. And this was also not a problem regarding the quality. I had to reconfigure, for example, sampling parameters because rewrite is a skill where we need creative sampling. And creative sampling by default is not available through Eagle. There is some additional paper was needed to be implemented on top of Eagle to be able to specify temperature greater than 0. After we did all of that, I have seen that we just needed to make some additional adjustment because the distribution of the next token changes after we apply the draft model. So, for example, hard-prone solutions all needed to be tweaked. But other than that, the quality hasn't dropped, at least with respect to our evaluations, which I have presented.
Yep, thank you. Then the next batch of questions. Sorry, I'm not sure I'm completely aware of the technical terminology, so I might confuse something. How did you deploy this file model and all the optimizations to the NPU? Was it execute torch or next runtime? How easy was the integration of these optimization techniques to the inference framework?
Yeah, the inference engine is the next runtime. This is true. And so on Next Runtime team is the team we collaborating with. And thanks to them, for example, we have applied grouped query attention, which was not available in ORT for Intel chips. And we had to make some feature requests. And thanks to this collaboration, currently for Silica is available on Qualcomm, Intel, and AMD NPUs. For me as a developer of Freeride, I am kind of, you know, hardware provider agnostic, so I do not really see the difference between inferring it on Qualcomm or Intel because of it is all hidden within the ORT. And the only thing which we see some discrepancy between platforms is, for example, when we add new feature like the speculative decoding. Usually it is first available with Qualcomm because Qualcomm is the provider for Microsoft Surface lineup. And so these collaborations has proven to be the most kind of optimal for us. And after that, we are starting to integrating it to other providers too. But yeah, in short, ORT is the main inference engine. Yeah.
Thanks. And then we have a question from or two questions from Diego. The first one is whether rewrite is multilingual, and the second one, so if it's possible to answer and it's not under some restrictions, how big is the team that works on rewrite?
So we have 7, let's say, most popular languages, tier 1 languages, for which we try to support every skill we are shipping. I believe they should be publicly available, like English, Chinese simplified, Portuguese, Spanish, and something else. Then we have like the whole team working on this small language models work stream is maybe 50 plus people. And regarding rewrite, for a long time, I was the only person driving the quality perspective of the skill. Now I have some headcount helping me with that, but it's a very small team basically. I know that in the cloud model rewrite, the team is notably bigger because it is shipped together with Microsoft Copilot, and it's kind of more important for the company.
All right. Thank you. Thank you for the answers. Do we have any questions that our guests want to ask using the microphones? Okay, doesn't look like this. Then probably I'll just ask the last question from my side. And maybe I've missed it totally, but my question would be if so you somehow account for user feedback and user actions when you work with this model, or once it's deployed, you update it according to your own preference and understanding. So essentially, how do you do this?
Mhm. Currently, yeah, we have the feedback with, let's say, upvoting, downvoting of our produced rewrites. We are trying, let's say, to eyeball through some of the examples due to some restrictions. We, for example, do not have the access to all the telemetry.
Mhm.
Yeah, and but we are able to see, for example, the lens distribution, and from that we see that, for example, users do not usually trigger rewrite for 1,000 or more tokens, which is a good thing for us, basically, because we struggle with longer input sequences. And from the quality perspective, we are using the data sets from our partners. Like, for example, some emails domain from the Outlook is used in order to retrain this. Yeah, but this is not like the pure, let's say, not the
Mhm.
pure feedback from the users. Yeah.
Okay, then thank you so much, Marat.
Thank
Don't see any more questions. So I think that would be it for today. And let's thank Marat again and wrap it up here.
Thank
Um,
you very much.
yeah, just the last note from the organization part. There is a question in chat whether there would be a link to the recording. Yes, the whole thing would be published on YouTube, and stay tuned with our Discord for updates. Okay, then thank you everyone for attending and see you next time.
See you.